Today I would like to present my presentation. My name is Dan Lei from class Math 3, and the subject I would like to present today is appreciation of mathematics. The course of this subject is Mtes 1132, and my natural name is Muhammad Safwan bin Jafar. This is the content of the presentation today. The first is introduction of this subject and mathematical foundation of machine learning, linear algebra in machine learning, probability and statistics in machine learning, calculus in machine learning in real-world application, mathematics as a fundamental element in machine learning, conclusion, and the last one is reference. Machine learning, a mathematical application in computer science. Machine learning (ML) is a branch of artificial intelligence (AI) that enable computer to learn from data and make the prediction or decision without applied programming. Mathematics plays a crucial role in machine learning by providing the theoretical foundation and those necessary for developing model and algorithm. This paper explores how mathematics support machine learning in real-world contexts and evaluate its fundamental role in understanding and advancing the field of computer science. Mathematical foundation of machine learning. Mathematics is at a core of machine learning, providing essential concepts and techniques for data analysis, model development, and optimization. The primary mathematical disciplines that contribute to machine learning include linear algebra, probability and statistics, and calculus. Linear algebra provides the foundation for handling multi-dimensional data, performing matrix operations, and implementing machine learning algorithms efficiently. Machine learning that with uncertain and noisy data probability help quantify uncertainty, while statistics ensure model reliability and performance evaluation. Calculus is essential for optimization, which is key to training machine learning models. It allows us to compute gradient, adjust weights, and minimize loss function. First, linear algebra in machine learning, vector and matrix. The data in machine learning is often represented as vector, which is 1D arrays, or matrix, 2D arrays. For example, an image can be stored as a matrix of pixels, volume in neural networks, weights, and activation are stored as matrix. Second, matrix multiplication. Matrix multiplication used in transforming data, feature engineering, and model computation. For example, in deep learning, multiplying the input data matrix with a web matrix can help compute activation in each layer. In engine values and engine vectors. Engine volume and engine vector used in princi- principal component analysis (PCA) to reduce dimensionality by identifying the directions in which data varies the most. It helps in compressing high decision dataset while preserving important factors. Probability concepts in machine learning. Probability distribution. Many machine learning models ensure that data follow a specific distribution such as normal distribution and Bernoulli distribution. For example, the normal distribution is commonly used in probabilistic models like Gaussian mixture models (GMMS). Random variable. A variable whose possible variants are outcomes of a random phenomenon. For example, in spec detection, the email content is randomly variable with volume corresponding spec or no spec. Expectation and variance. Expectation mean used to find the variable predict outcome, whereas the spread of data point from the mean. These two can help to evaluate model consistencies and bias variance trade-off. Statistic concepts in machine learning. Descriptive statistics. Measure of central distances used to find the mean, medium, and mode. Measure of spread. Find the variance, standard deviation, and range. Used to summarize the data before training a model. Invariant statistics. Hypothesis testing. Hypothesis testing used to determine whether data patterns are statistically significant, and confidence interval used to estimate the reliability of model prediction. Then p-value used to determine if a feature is important in a dataset. The last one is regression analyzing. Linear regression used to fit a line to predict continuous value. Logistic regression used to classify outcomes using probability. Then polynomial regression model nonlinear relationship. Calculus in machine learning. Derivative and gradient. A derivative measures how a function changes with respect to an input. The gradient, a vector of partial derivatives, indicate the direction of the steps ascent and or descent. Fs equal to s power 2. The derivative is equal to 2s. When s equal to 2, the derivative is 4, meaning the function is increasing at that point. When s equal to negative 3, the derivative is equal to negative 6, meaning the function is decreasing at that point. Graphical interpretation. When the derivative is more than 0, the function is increasing. If the derivative less than 0, the function is decreasing. Partial derivative. Partial derivative used in multivariable function to compute gradient for each parameter separately, essential in training machine learning models with multiple features. This is the concept of partial derivative and the explanation for the concept. Partial derivative used to measure change in a function WRT one variable gradient. The vector of partial derivative linear regression used to compute gradient for web neural networks. Compute gradient in backpropagation. Machine learning in real-world application healthcare. Machine learning models use statistical analysis to and probability theory to detect disease, predict patient outcomes, and optimize treatment plans. For example, deep learning models analyze medical images using convolutional neural network (CNNs) to identify tumor and anomalies. CNNs process medical images such as X-ray and CT scan to identify pattern associated with diseases such as cancer. Next, finance. In financial market, machine learning algorithms utilize statistical models to detect fraudulent transactions, predict stock price, and automate trading strategy. Time series analysis, a branch of statistics, is widely used for forecasting economic threats. Fraud data using machine learning in markets, for example, credit card fraud detection. When analyze real-time transaction data such as location, amount, time, and frequencies. Natural language processing (NLP). Machine learning techniques in NLP rely on linear algebra and probability to analyze and generate human language. Word embedding such as word use vector space representation to capture semantic relationship between words. Computers cannot process text directly, so NLP models convert words into numerical representation using vector space, a concept from linear algebra. Each word is mapped to a multi-dimensional vector where similar words have closer distance in this space. Autonomous vehicles. Machine learning powers self-driving car by processing sensor data using probabilistic model and reinforcement learning. Algorithms use Bayesian network and Markov decision process to make real-time decisions. Camera can detect lane making traffic signs and pen- pedestrian GPS and email can provide precise location tracking. E-commerce and recommendation system. Recommendations algorithm leverage matrix factorization technique from linear algebra to predict user preferences. Collaborative filtering and deep learning models help personalize content for users on platforms like YouTube and TikTok. YouTube use neural network to predict videos user might watch based on past interaction. TikTok use reinforcement learning and deep learning to continuously recommendation. Model development and interpretation. Without mathematical principle, it would be difficult to develop models that generalize well to new data. Concepts such as loss function, regularization, and optimization ensure that models perform effectively. Loss were used to measuring model performance. Regularization used to prevent overfitting. Optimization used to find the best model parameters. Algorithm efficiency. Understanding the mathematical complexity of algorithm helps optimize computational resource. The time and space complexity of machine learning algorithms are analyzed using mathematical techniques to improve scalability. Time complexity used to measure execution speed. Space complexity used to manage memory user. Explainability and interpretability. Mathematics provide tools to interpret machine learning models, ensuring transparency in decision making. Technical like sharpest additive explanation and line local interpretable model agnostic explanation use probability and game theory to explain model prediction. Regulatory complex. Many industry require interpretable AI model, for example, used to in finance and healthcare. Yes, detection. Yes, detection help identify and correct unfair or discriminatory model behavior. Debugging models. Reverse errors and ensure reliability. Use trust. Build confidence AI driver decision. Theoretical advancement. Continuous research in mathematical theory leads to development of new machine learning methodology. For instance, breakthrough in deep learning architecture stem from advancement in optimization and linear algebra. For example, image data represent as a tensor 3D matrix of species. Conclusion: Mathematics is a backbone of machine learning, providing the necessary theoretical and computation tools for model development, optimization, and interpretation. It supports a wide range of real-world applications from healthcare to Venetian and autonomous system. Understanding the mathematical concepts enable researching and practitioner to build efficient transparent machine learning models. This is the reference I use when I do this PPT. That's all for today's presentation. Thank you.